Okay. Hello, everyone. My name is Ajay Jacob, and I am the Director of Projects at the California Dreams Hub. It's my pleasure to invite Professor Eli Levinson-Falk. He's a professor at the Department of Physics and Astronomy at and the Ming Sing Department of Electrical and Computer Engineering at the University of Southern California. He runs the LFL, which is Levinson-Falk Laboratory. It's an experimental research group that focuses on using superconducting electrical circuits for quantum information applications. He received his PhD from the University of California, Berkeley in 2013 and conducted postdoctoral studies at Stanford University. It's my pleasure to welcome Professor Levinson here, and the stage is yours, Eli.
Thank you for the invitation. Thank you for the introduction.
Your volume is coming very less.
Oh, is this better? Is it coming in now?
It is not coming up good.
Okay, hold on 1 second. It was fine while we were doing check, of course. Me again?
Yes.
Okay. So thanks for the invitation. Please do stop me at any point through the talk with questions. We're going to cover some stuff that I think is going to be quite different from what most people are used to, and I really like to get the discussion going. So first, I just need to acknowledge all the people who did the work on this project, most notably my student Melita and Professor Daniel Lidar's student Sarov. Melita did the majority of the experiments. Sarov did the majority of the numerics. My student Evangelos, who's since graduated, did some work at the beginning of the project to set up the experiments. If you're interested to read the paper, here's the citation. You can just scan this QR code to get there. All right. So we're talking about quantum sensing here. Essentially, boiled down to the simplest description, I'm going to say there is some environmental variable, something in the environment I'll call B. Could be like a magnetic field, could be a temperature, doesn't matter. And in order to detect it, I'm going to make a quantum mechanical wave function somehow depend on that variable. That's the quantum part of quantum sensing. Now, typically, you're doing this using some interference effect. Maybe you're entangling things with each other. You're doing some non-classical states of light. But one very common approach is you're changing the Hamiltonian of the system so that it depends on B. And the Hamiltonian is what governs the time evolution of the quantum state. So this is what tells you, how the state is going to behave as time goes forward. If you change the Hamiltonian, you change the state, and that gives you this dependence. Now, there's a challenge here, which is decoherence, essentially random interactions with the environment that you don't control, and they sort of scramble this time evolution. So if you go and do it again, you'll get a different answer. And this is a problem because you're supposed to be doing this many times to build up SNR. Build up signals-noise ratio. I'll use that acronym a lot, SNR. So people have worked on all sorts of solutions for this. You can always just average more to improve your signal-to-noise ratio. You can try to design a better sensor just so that this derivative, this sensitivity of this transfer function is higher. You could really try to reduce decoherence through some sensor design. There's all sorts of clever detection schemes that can maybe reduce some of the coherence or improve sensitivity in some cases, or quickly lock in on certain types of signals. There's all sorts of fancy stuff that's been done. Almost all of it is, I will say, particular to a type of sensor. It's particular to a certain technology. It's working on the sensor itself. What I'm going to be discussing here is a protocol that I think is fairly sensor agnostic. It's going to work for a very, very broad range. Now, I know we've got a little bit of a mixed audience. I'm going to give a extremely quick introduction to the quantum mechanics concepts that we need for this. If you're familiar with quantum info science, feel free to check your email. I will tell you when it's time to pay attention again. So in quantum mechanics, we're going to take the simplest possible system, a quantum bit, a qubit, where there's only two states, 0 and 1, and we can put them in superposition. where alpha and beta are complex coefficients. So this is our quantum state. It's some linear combination of these two. And we can just write that as a column vector with coefficients alpha and beta. If you go and do a measurement, the probability that you measure the qubit to be in the 0 state is the mod square of alpha. Probability you measure in the 1 state is the mod square of beta. But that's only if you are measuring 0 versus 1. That's not the only thing that you have to measure, or the only thing you're allowed to measure. You can also measure essentially in a different basis. So the math behind a quantum bit is the same as the math behind a physical spin, like a massive spinning object with what we call spin 1/2, a particular amount of angular momentum. And these measurements in other bases essentially correspond to measuring the projection of angular momentum along different axes. And the math that governs this is governed by the Pauli matrices, sigma x, sigma y, and sigma z, which are just these 2x2 matrices shown here. And essentially what you're doing when you do a measurement is saying which of the eigenstates of this matrix, which of the eigenvectors does my measurement project to? So if I'm doing a measurement of z, I say, okay, I'm trying to measure that I'm in one or the other eigenvector of this Pauli matrix. Well, that's just 0 or 1. If I'm doing a measurement of x, it's one or the other eigenvector of this matrix, which is 0 plus 1 over root 2, or 0 minus 1 over root 2. And again, in quantum mechanics, you're always going to get one of those answers. If I do a measurement of x, it doesn't matter what my initial state was, I'm going to project to one of these two states. Likewise, if I measure y, it's the same. It's just 0 plus or minus I times 1 over root 2. I here is the square root of -1. I'm a physicist, not an engineer. That means I use I for that and not J. All right. So this is just very, very standard quantum mechanics. There's one tool that we need to look at, which is a way of representing the state of a qubit, and it's called the Bloch sphere. What we do is we make a classical 3D vector out of the quantum state. And what we have is that its x, y, and z components, the vector's components, are the expected values of measurements of each of these quantities. So what you say is that, okay, if you measure the first basis state, 0 for z, or 0 plus 1 over root 2 for x, etc., that counts as +1. If you measure the other basis state, you get -1. The expected value is the probability of measuring +1 minus the probability of measuring -1. And so you take these expected values, and those are just the x, y, and z components of the vector. And it's going to be somewhere on the surface of or inside this sphere. Now, if I have a sort of perfect, pure quantum state, like a state that, is the one that I've showed you before, then the length of this Bloch vector is 1. You're always sort of guaranteed that this vector is going to lie on the surface of this unit sphere. On the other hand, if I somehow completely randomize the state, like, you go to redo your experiment, and you've got a completely different thing going on, every single one of these probabilities is 1/2. You're just equally likely to get any outcome. So all these expected values are 0, and you have a length 0. And so this is a way that we can actually represent decoherence. We can represent randomness in the system. Now, typically, we're going to lump these into two processes. So here I'm showing an animation of what happens to a Bloch vector under these processes. Here are just the y, or I guess actually this is supposed to be x, and z components of the vector. We're going to say that there are two decoherence processes. The first one is what we'll call dephasing. You can think of this as the qubit getting randomly rotated about the z-axis. Essentially, what it's doing is, if you go back to the basis states, you can see this x basis and this y basis are only differing by this factor of I over here. That's a complex phase. And if that complex phase gets scrambled, then you sort of lose all the xy information. And so dephasing just shrinks the xy projection. There's also relaxation. This thing is in some state, but there's also some sort of thermal equilibrium. Uh, Typically, we're just going to assume that it's at very, very low temperature. So the thermal equilibrium is the low energy state, which we, by convention, say is zero. So it's just going to relax to zero. All right, so this is how we're going to talk about decoherence. Now we can make this just slightly more rigorous. If you were stopping your paying attention because you already knew all of this, I think it's time to tune back in because I think we don't actually go through this part enough when we talk about block vectors. The evolution of the block vector is governed by these simple differential equations, the block equations. These are just the time derivatives of each component on the left. This first term here, this is that dephasing decay here, or relaxation to the thermal state. And then these other terms are basically rotation about some vector I'll call little h, basically a Hamiltonian vector, sort of the influence of the universe on the system that's sort of repeatable and coherent and happens the same every time. And it just causes this vector to rotate about some axis at some rate. Okay, so this is just all the machinery that we need. Let's get back to sensing. One very common way to do sensing is that you somehow say, okay, this thing that's going to cause my qubit state to rotate about the z-axis, that's going to be the thing that I sense. So, I want to detect some environmental variable B. I will map it to this quantity delta. And this is what we call the qubit frequency. And the reason we call that is that if you put the qubit state in the xy plane on the Bloch sphere, it will rotate around in the xy plane at a rate delta. Assuming that's sort of the only thing that's happening to it, it will just rotate around in a circle. Now, this is something we can measure using an experiment called Ramsey interferometry. This is invented in 1950 for nuclear magnetic resonance. That's the animation that's going on here. I'll let it restart, but essentially what we do, okay, so we start in the ground state, rotate the qubit down to the xy plane, then let it evolve freely, so it rotates around at a rate delta, let it go for some period of time, and then rotate it back to this z-axis to do a measurement of whether it's 0 or 1. And in doing so, we essentially figure out where in the xy plane it was. Now, if you just look sort of top down at the xy projection of this, all it looks like is the vector sort of rotating around in a circle until you go to do the measurements. This is a very common way to do quantum sensing. It's also very important for calibrating your control of your qubits. So if you're doing quantum computing, which is most of what I work on, you need to know what the qubit frequency is. Basically, you need to know what this quantity is actually the energy splitting between the 0 state and the 1 state. And that's a very important quantity. Okay, so this is how you measure that. But again, we have dephasing and relaxation. They're trying to screw up the evolution of this Bloch vector. They're not letting it rotate. They're trying to project it back to the thermal state and get rid of all the XY information. Now, when you're doing these measurements, you always have to do them on some kind of ensemble. You're measuring the same system many, many, many times, or you're measuring some very large collection of systems all at the same time. Either way, you're averaging over many instances. And so on average, what this looks like is you have this Bloch vector rotating around, and sorry about the frame rate here. The Bloch vector is rotating around in a circle, but it's also decaying. And so the x and y components of this Bloch vector just shrink as a function of time. And so this, nominally hurts your signal to noise ratio if you're trying to figure out how fast it's going around. Now, generally, if that shrinking is slow, if you can get several oscillations in there, then it doesn't really matter. But on the other hand, what if it's rotating really, really small, or really slowly compared to how fast it's shrinking? So what if delta is very, very small compared to the rate of shrinking 1 over T2? Well, then you get the situation that I'm animating here. Here, black is the Bloch vector, and red and blue are just the x and y components of it. So it starts to rotate, but it's also shrinking the whole time. So x is shrinking the whole time, y grows for a while and then shrinks. And they're governed by these very simple equations. You don't need to worry too much about them, except to notice that the y component here ends up being linearly proportional to delta. Remember, delta was the thing we were trying to measure, and now it's mapping linearly onto the y component of the block vector. So let me just reframe the problem now. I want to measure Vy. I want to measure the y component of the block vector. I want to measure the sort of amount of the qubit state that lies along the different y-axis basis vectors. And I want to maximize my signal-to-noise ratio. Well, how do I do that? I can't just measure one time. I can't just measure one instance of my experiment because I'm guaranteed to get a value of, +1, it's on the positive y-axis, or -1, it's on the minus y-axis. That doesn't actually tell me what it was. I need to build up many shots to get the expected value. Now, the probability that I get a +1 is just this 1 plus Vy over 2. Probability I get -1 is 1 minus Vy over 2. And so I can say, all right, let me do this n times. And what I'll get is a difference in the number of plus shots versus minus shots of n times Vy. Now, this is governed by binomial statistics. There's two outcomes. And so it's very easy to calculate the standard deviation. And so you just take the ratio to get the signal-to-noise ratio. And we're going to be working in the limit where Vy is small. Again, we have small signals. And so approximately your signal-to-noise ratio is Vy times the square root of the number of shots, the number of times you're repeating this experiment, or the number of systems that you're doing it on simultaneously. Now, this is the thing we're trying to maximize. And the key is we really need to maximize this overall quantity, not just Vy or not just n. We need a protocol that maximizes that. And exactly how we do that depends on details of the experimental apparatus. The idea is that, okay, while we're sort of acquiring signal, while the qubit is evolving and sensing the environment, it's going to be doing that for some time t. But then, I do a measurement, I have to somehow reset it and prepare it again. And that's going to take some time ti, some idle time. And if I have a total time t that I'm allowed to do this experiment, I've got deadlines or whatever, then the number of shots I get is big T divided by little t plus ti. And so this is the n. Therefore, the thing I'm trying to maximize is Vy over the square root of t plus ti. Okay, so let me just step back for a second and make sure that we are still on the same page. I am still trying to detect some environmental variable. I haven't said what the environmental variable is. It doesn't really matter as long as it maps to this qubit frequency. I have reduced the problem then to detecting this quantity, to maximizing this quantity, sorry. Detecting Vy while maximizing this quantity. Now, in general, this can be kind of messy. I'm just going to look in two limits. I will look in the limit when Ti is very large. In other words, it takes a lot of effort to set up a shot. You only get a fixed number of shots per unit time. So then you just need to maximize Vy. And in that limit, if you do this sort of standard Ramsey sequence, you maximize Vy when a time has gone by equal to T2, equal to this sort of characteristic decay time. And the amount of signal that you get is T2 times delta times the signal we're trying to detect divided by E, the natural logarithm. On the other hand, what if there's like no cost at all to setting up a shot, that it doesn't take you any time? All of the time in the experiment is actually spent with the qubit freely evolving. Well, then if you let it evolve longer, it might be picking up more signal, but it's doing that at the cost of you have to take fewer shots because now you're using up that time. And so in this case, you're maximizing Vy over root T. Again, for Ramsey, it's very easy to solve when that's sort of maximized. It's at T2 over 2, and it gives you this quantity for Vy. Again, E here is the natural log. Now, I'm talking about the Ramsey protocol because this is how it has been done since 1950. This is how you detect qubit frequency until someone proposes a different protocol. And you have to know whether that protocol is better or worse than Ramsey. So what I'm going to define are these two ratios, RV, for the ratio of Vy and Rs for the ratio of S and R in this case, which is just sort of what your protocol does for Vy or Vy over root T divided by what Ramsey does for those quantities. And so the idea is if RV is equal to 1, your protocol is exactly the same as Ramsey. If RV or RS is larger than 1, you are doing better than Ramsey. You have better SNR than Ramsey does. If it's less than 1, you're doing worse, so you should go back to the Ramsey sequence. All right, so now we have this question, how can we do better? And again, let's look back at what happens to a qubit state under decoherence. In particular, let's say there's relaxation, and that relaxation is happening at some low temperature. So it's going to the ground state. Okay, random stuff is happening to the qubit, but we know where it's going. We know it's going to land in the ground state. And so we're actually gaining information about the Z component of the block vector. We're losing the X component and the Y component. We're losing that information, but we're gaining Z component information, and we can use that. So now we come to the sort of meat of the protocol. I do want to pause just for a second here and see if there are any questions.
No questions yet.
Okay. So this is now a protocol that my collaborator, Daniel Lidar, worked out many years ago as sort of a toy model for his open systems class. And it wasn't until we sort of got into the experiments that we realized how incredibly useful it could be. So we call coherence stabilization. And it's more general than what I'm going to explain, but I'll give you sort of a simple case of it. Let's say we start at t equals 0 with the block vector in the xz plane. So it has no y component. It's somewhere between the z-axis and the x-axis. And we're going to drive it with some Hamiltonian that only has a y component. So it's going to rotate about the y-axis. So it's in the xz plane, and then it's rotating in the xz plane because it's rotating about y. In that case, the block equations look like this. You know, we have our decoherence terms. We have our thing that we're trying to sense, our delta. And then we have our coherent drive causing these rotations. And you know, the details of these equations are not super important. What is important is I can say, okay, well, these are the time derivatives on the left. Let's say I want one of these things to not change. I can just put a 0 on the left and solve for hy. Hy is something I have control over. It's something I'm doing as an experimentalist. And so it's very straightforward. If I want Vx to not change, I just set this to 0 on the left. And I find that hy needs to be equal to the initial value of Vx divided by 2t2 times the value of Vz. So it is going to be time dependent. Vz is changing. But you can make this, you know, constant. You can make Vx not change as long as Vz is not 0. You know, if Vz is 0, this thing blows up and you can't do it anymore. And this is where I come back now to this fact that as the qubit relaxes, we know where it's going. Vz actually grows in this equation. It's 1 minus Vz times this, not just minus Vz. And Vz is always less than 1. So there's always a positive number here. So it's always growing. And that growth is basically something we can use to sort of replenish the shrinking that's happening on Vx. And in fact, if Vx is less than 1/2 the square root of t2 over t1, the sort of ratio of the overall coherence time to the relaxation time, then you can stabilize this thing forever. Now, if it's larger than this, if you're trying to stabilize a larger thing than this, there will be some time at which you can no longer stabilize it. We call it the breakdown time. It's going to depend on what state you're trying to stabilize. It's going to depend on the ratio of T1 and T2, and it's just going to scale linearly with T2. Now, what does this look like? Again, let me show you what it looks like if we weren't doing anything. This is just standard decoherence. Again, we sort of lose information on the x-axis. We gain information on the z-axis. It goes back to the ground state. If I run my stabilization protocol, on the left, this is sort of like the y drive. This is hy that I'm doing. And on the right, these are those block components. you can see that the x component, this stays constant. Now the z component is rotating down. It's being rotated by this y drive. And I've cut it off just before it breaks down here because it's just about to hit 0, at which point our protocol is not going to work. So this is a case where I do have a breakdown. On the other hand, if I'm trying to stabilize a slightly smaller value, I can stabilize this thing forever. All right, now I am an experimentalist. We're already on slide 17. I haven't talked about experiments at all. I've only done theory. But here is the experiment. We actually can do this. It works quite well. So what I'm showing here are just, x, y, and z components of the block vector in an experimental measurement. This was done with a superconducting qubit, but could have been done with any quantum system. And on the left, we're stabilizing a state that's not permanently stable. We have a breakdown because we rotated the block vector until the z component was 0, and then we just had to stop. So from here left, that's being stabilized. From here right, this is sort of what would happen if we just left the system alone. At this point, we're basically just turning off the control. On the right-hand side, we tried a slightly smaller value of Vx, and we could stabilize it forever. Now, I want to point out in both cases here, the T2, the sort of overall decoherence time, was about 75 microseconds. Here, I stabilized the thing for 150 microseconds. Here, I've stabilized it for 350, and then I got bored and stopped. And this would keep going forever. So we can do this. We can stabilize one component of the block vector. I was talking about quantum sensing. Let's see what this does now when we have sensing, when we have something to sense. So we're trying to sense this delta, what we call a detuning. And let's look at what happens now to the y component. So in blue here, I'm plotting, again, the standard Ramsey protocol. And in pink, I'm plotting what happens with this coherent stabilization protocol, the same two states that I just showed you here. And what you can see very clearly is that in the stabilization protocol, Vy grows to a larger value. Now, it doesn't get there quite as fast. You'll notice that the blue one is growing a little bit faster at the beginning here. So there's a little bit of a tortoise in the hare kind of effect. Your stabilized protocol has a Vy that grows a little bit more slowly, but it keeps doing it for longer. And it clearly gets to a larger value. So we saw this and we're like, okay, cool. This can be useful. This can be used for quantum sensing. Let's figure out how to do it as well as possible. Let's figure out how to optimize this. The easiest case to solve is the case where you have this Vx that you can stabilize forever. Because then you just say, okay, I know what Vx is. Vy just ends up being this really simple delta times T2 times Vx. So you can very easily solve it. It's just 1/2 delta T2 times this ratio square root of T2 over T1. Now, that gives you then an RV, a ratio of how large this Vy is compared to a Ramsey measurement of E over 2 root T2 over T1. T2 is bounded by 2T1. That's the largest it can possibly be. So if you're in that limit, you get E over root 2, which is a factor of 1.92. So it's nearly a factor of 2 improvement in the signal that you're getting. Now, it's signal, not signal divided by root T. It's growing slowly, remember. And this is maybe not the best you can do. So we look at the case now where we're stabilizing a state temporarily. We can stabilize it for some period of time, and then it breaks down, and we have to just let it go. And that's what I'm sort of plotting here on the right. Again, black is the sort of overall XY projection of the block vector. Red is the X component. Blue is the Y component. Ignore the equations on the left. Just look at the graph for a minute. I'm going to say, okay, stable, stable, breakdown, right there. Let's watch it again. It's stable, breaks down. Now, if you watch it and look at the blue arrow, breakdown, it kept growing a little bit. Right after breakdown, it keeps growing for a short time. So you're actually better off using a state that has a breakdown, using something you can't stabilize forever, and letting it break down and then waiting a little bit and then measuring. And so we can solve for sort of when you get the best Vy, when you get the largest Vy, or when you get the largest Vy over root t. And we do this in terms of when the breakdown time is. All these equations are sort of in terms of the breakdown time. We can solve analytically for what the breakdown time is as a function of what the initial state is. That's a really complicated solution, but luckily Sarav's good at theory and he solved that. And then we just sweep over initial states to see how we can improve things. So again, this is so far all theory. Here are the results. So again, this is RV. This is the ratio of how much signal we get compared to Ramsey. RS is the ratio of how much signal per root time we get compared to Ramsey. Initial state here, this is basically saying the angle to the z-axis. So over here is exactly on the x-axis. Over here is exactly on the z-axis. Ramsey protocol is when you start exactly here. And what we can see is that for a broad range of states, there is an RV value and an RS value that is above 1, where we have a boost compared to Ramsey. Now, the boost is larger if T2 over T1 is larger, if T1 over T2 is smaller, if it's sort of limited by this minimum value of 0.5. Essentially, the less relaxation you have, the less you sort of know where the qubit has gone, you know that it's gone to the ground state. And so the less effective it is, but it's still effective. So in the case where sort of you get the maximum improvement, where you're completely limited by relaxation, you can get a 1.96 times improvement compared to Ramsey in the Vy, in the SNR per measurement shot, or 1.184 in Vy over root t, in the SNR per root evolution time. But even in the case where there's no relaxation, even if I don't get this benefit of knowing where the qubit is, this sort of tortoise in the hare effect still gives me some boost. And I get an RV of 1.09, RS saturates to 1. It just saturates back to Ramsey. And we can see that here, just plotting RV and RS as the maximum values that we could get, picking the right initial state, as a function of this T1 over T2 ratio. This curve obviously comes down, but it saturates to 1.09. This one saturates to 1. In both cases, we're doing at least as good as Ramsey. So we have an unconditional enhancement of SNR. And I want to point out this limit on the right, where shots are completely free, it takes no time to set them up, is not really physical. There's always some cost. So you're always going to do at least a little bit better than Ramsey. Okay, that was all a lot of theory claims, but it really does work. So here are those exact same plots. Here is the sensitivity of Vy versus, basically we altered delta, we altered this detuning signal we're trying to pick up, and look, that's the slope of Vy versus that. That's basically our sensitivity. And took the ratio to what we got measuring with Ramsey for RV, the ratio is divided by root t for RS. And in both cases, we get these curves that spend a good amount of time above 1. These dashed lines here, the dots here are data, for a given initial state, what was the RV or the RS that we got. The vertical lines are the error bars, that's 2 standard deviation error bar. And the dashed line is not a fit. It is a prediction. It's completely, parameter-free prediction. The only input that went into it is that we measured T1 and T2 for this qubit, and it got a ratio of about 0.8, and we just put that in. That's what generates this curve. So it works. It really does work. And importantly, it works even if things aren't perfectly calibrated. So we simulated this. What we've done here is taken the situation where we've measured T1 and T2, and we've set up our protocol, and we're starting to run it, but maybe they changed in the background, T1 or T2 changed, or maybe we just measured them wrong in the first place, whatever. We're doing something wrong. So we're doing control for a particular value of T1 and T2, but the system has different values. And so we've simulated this. If you're sort of perfectly calibrated, that's where this point right in the middle, and we define that to be the white color, Here we're just sort of simulating RV and RS for the case where T1 equals T2, where the ratio is 1. If, on the other hand, 1 over T2 is larger than we thought it was, so the decoherence rate is larger, that's up here. If it's smaller, that's down here. 1 over T1 being larger is over here, smaller over here. Red is a higher value, blue is lower, so sort of red is better, blue is worse. And really what I want to point out here is that if you go along diagonal lines where T1 over T2 is actually constant, this is almost constant. It's really just depending on T1 over T2, which is actually just controlling how well the protocol works in the first place. It's not depending on the miscalibration, really. You can be very, very miscalibrated. You can have both T1 and T2 off by 20% and essentially get exactly the same response that you were getting before. Now, it's not 100% perfect. You'll notice in the upper left corner here, there's a small area where it actually drops below 1. That's, again, the effect of this miscalibration. But the majority of the effect is just, the larger T2 over T1 is, the better your signal is. All right, so this is the protocol. And I really want to give you the sort of why we think this is exciting. Absolutely nothing about what I was saying was particular to superconducting qubits. It will work with just about any system as long as you can do a Ramsey measurement, as long as you can do a continuous control and a Ramsey measurement. And generally, if you can do Ramsey, you can do a continuous control. So you get an unconditional enhancement in signal-to-noise ratio. And you don't need any extra experimental resources. You don't have to do anything fancy. You don't need to measure and really quickly do feedback. You don't need auxiliary systems. You don't need to change how you're doing your measurements. So this really should work in a very wide variety of systems. So I just got a Q&A that I will respond to quickly. I'll respond to just in a moment. Now, this protocol works best when all of the decoherence is coming from relaxation, when sort of T1 is what's limiting you, and when you're either relaxing at 0 temperature, so it's sending it deterministically to the ground state, or actually it could be at any temperature as long as you were starting in that same thermal state. I won't go through the math on that, but essentially, as long as the place that the relaxation takes you is the same as the place that you started, this works really well. Now, on the other hand, if you have a very high temperature, you somehow do good initialization of your state so that it's effectively a low temperature when you start it, but then relaxes to a high temperature, then this protocol doesn't work as well. On the other hand, it might be worth doing something that actually worsens coherence just to decrease that temperature so that this protocol can work. I will say it's probably only worth it if it improves something else, like maybe it gives you a faster reset or something. Now, the protocol I've shown you is not yet optimal. It is optimal given that we're doing coherence stabilization, but it's definitely not optimal of all controls that we could possibly do. And I can prove it really, really easily. In all cases, the sort of optimum time to do a measurement was slightly after the coherence stabilization finished, after the breakdown time. And during that time, VZ grew a little bit. We got a little bit of relaxation that gave us a little bit of information about the Z component of the qubit. We don't use that information. We could, but we don't. So I can, immediately say a protocol that uses that information would be better. Now, probably there's some overall protocol that doesn't do coherence stabilization at all, but looks vaguely similar and is truly optimal. So this is something we're planning to look into. We'll sort of use these coherence stabilization controls as the seed and then use numerical gradient descent methods to fully optimize. Now, The thing that I'm showing you is detecting a constant value of delta, a constant qubit frequency. Oftentimes, we actually have a thing we're trying to detect that is oscillatory. Delta is itself oscillating in time. And you want to be able to sense that. Well, we're pretty sure that we can do that. We just need to get the qubit state to oscillate in the same way, but it probably shouldn't be oscillating right along with it. Typically, what people do is they'll sort of leave it on this side of the Bloch sphere for a long time and then immediately slam it over to this side, kind of like a square wave control. It's called bang bang. We think that's probably incorrect in terms of optimality, because if you have a sinusoidal signal, when it's crossing through zero, there's no signal to look at. So you should put your qubit somewhere that it's not getting decohered in the meantime. So we're going to try sort of combining this with other techniques like feedback techniques, like dynamical decoupling techniques, and see really how far we can push this protocol in some cases. Now, there was a question in the Q&A about doing this with multiple qubits. And let me say that if you have multiple uninteracting qubits that don't know about each other, this looks exactly identical to what I've just done. The experiments I showed, I was using one qubit over and over and over. It looks exactly the same to use many qubits simultaneously if they're not talking to each other. If the qubits are interacting, then you can create these entangled states between them. You can create a state that encompasses all the qubits and cannot be described only by one qubit at a time. In that case, you can get a sensitivity boost in many protocols. There is a generalization of coherent stabilization that would work for entangled states. What we haven't shown yet is whether it gives you a boost in sensing versus the equivalent of Ramsey for an entangled state. And this is work that we're planning to do going forward. All right, so that's pretty much everything I have right now. I think is a good place to stop and take further questions.
Thank you, Ray. Great talk. Quite a number of fundamentals to follow up. We will go to the questions. So Shripriya has a question. Shripriya, maybe you can come to the mic and ask the question.
I think that's the one that I was just answering, actually.
Yeah. Oh, yes. Okay.
Yeah.
So I have one question, Eli. So this is a system, and how about what parameters do you have to keep in mind when you have to package the sensor?
So let me say that the packaging that you're doing will affect coherence times. And obviously, longer coherence is basically always better. That's just an easy way to linearly scale your sensitivity if T2 is long.
Yes.
It might affect the temperature. And in general, low temperature is better. The whether it relaxes more and more to its low energy state is better. Although, really, really depends on the details. And also it might affect the control. It might affect how much you are able to do this kind of continuous control, these continuous rotations that are required for this protocol. All that said, nothing about the protocol itself says anything about the hardware. It just says, do this control to your abstract two-state quantum system and it will work. And we did it on a real one, but the real one had nothing special about it. It was just sort of a very standard superconducting qubit. It could have been done on an NV center, on a silicon spin, on a trapped ion. It really doesn't matter.
I do have a few more questions, but I will wait for others to ask questions. Jay has a question. How does this protocol compare to Han echo, or is this one of the techniques you would like to combine with?
Yeah, so Han echo is sort of a special case of a broader class of protocols called dynamical decoupling, where essentially you have the qubit state on the Bloch sphere, it's evolving in some way, and then you deliberately flip it over to the other side. And this kind of lets it undo whatever evolution was happening constantly. Now, if whatever's causing the evolution also flips, say because it was some time varying signal and you flipped it at the right time, then you sort of cancel out all the constants, but you let this time varying signal build up. And so this is how these protocols work. You sort of flip back and forth, maybe in some complicated way, at the right rate, and it makes you sensitive to signals in some band of frequencies that corresponds to sort of how fast you're flipping, how often you're flipping. Hahn echo is just a special case where you only flip once. So it basically cancels out things that are completely constant, and only looks at things that are changing sort of on the frequency scale of the flip time. You know, if you let it go for a while, flip it, and then let it go for the same amount of time, things that have that period are going to be enhanced sensitivity. I will say that in many applications, like in nuclear magnetic resonance, they're not looking at delta often. So like magnetic resonance imaging, MRI, they're typically actually measuring T1 and T2. And in those cases, something like Hahn echo is preferred because it gets rid of a lot of the low frequency noise, and it gives you a more sensitive measure of the high frequency T2. But if you are looking at, if you're trying to look at a constant detuning, Hahn echo gets rid of your sensitivity to that, so that's no good. If you're trying to look at a constant delta. If you're trying to look at a time varying delta, Hahn echo or some dynamical decoupling sequence can sort of help you eliminate sensitivity to everything except that frequency window. And what I'm saying with our protocol is that there should be a generalization of what we're doing to a similar approach where we're stabilizing ourselves in a way that we are sensitive to a particular frequency band of signals.
Thank you. Is there any more questions? Sri Priya has her hands.
Yes. Hi, Dr. Ajay. Hi, Dr. Eli.
Hi.
I just wanted to say this is a very interesting and clear talk. My question has to do with a comment that you had made earlier that this technique is effective whether using superconductive qubit or silicon spin qubits. I'm not an expert in this field, but what I wanted to ask is, what makes this particular technique agnostic to the type of qubit, and does the rate of decoherence have any effect on the fidelity that you're able to achieve, ultimately, or is that something that matters for quantum compute but not for quantum sensing?
Yeah. So let me say first that a better sensor is always better. And some technologies are just better at being sensors than others. Superconducting qubits, in fact, are typically very, very bad at being sensors because we put an enormous amount of effort into making sure they do not detect their environment, because we're usually using them for quantum computing. We want them not to have any environmental sensitivity. If you're improving the coherence of a particular sensor, you've always made it better. You've just always improved its sensitivity. Regardless of what protocol you were using, you've always improved things. That would be true if you were doing Ramsey. That would be true if you're doing our protocol. Our point is, regardless of what the decoherence rate is, regardless of how long it stays coherent, using our protocol will give you a better sensitivity than using the Ramsey protocol. Now, what makes it sort of agnostic as the sensor, what makes it not depend on what type of sensor it is that the only thing you really need are, the fact that your signal is the detuning between two states, the energy splitting between two states, and the ability to do this continuous control. And those are both extremely, extremely, extremely common, common to many, many different types of sensors. Now, I will say for some technologies, this protocol will give you a larger boost And for some technologies, it will not give you a very large boost. Essentially, it depends on how much the system has relaxation, how much T1 is less than infinity, and how much that is relaxing sort of back to the same state that it was started out in when you started your experiment, versus it's relaxing to some completely scrambled state. So that's basically temperature. So if you have low temperature and short T1, or at least if you start in a thermal state and you have short T1, that's when the protocol works really well.
Okay, that makes a lot of sense. Thank you.
So when we think about sensors, today we have started thinking about distributed sensors, and especially from an edge point of view, quantum edge sensors. What is important is the entanglement.
Mhm.
And how can you entangle these sensors for long range sensing? And not long range sensing, but for distributed sensing.
Yeah.
In a long range, yeah.
Yes. So I will say that in a standard protocol, the entanglement can be set up many, many different ways. It really depends on the type of sensor. Often, if you're trying to do something long range, you're using photons. And so what you're trying to do is, say, take two atoms that are far apart from each other, put one of them in a superposition of states where one of those will emit a photon and one of them will not. Catch the emitted photon if it does, and send it over to this atom where it gets absorbed. And so that gives you a superposition, an entangled state of this atom sort of not able to emit a photon anymore, and this one having one, versus the other way around. But that's just one very, very simple example. There's much more complicated and subtle protocols. The thing I'm talking about actually is not really, that doesn't really care about how you set up that initial state, how you generate that entanglement in the first place. The question is, what do you do next? What do you do when the signal is actually coming in? The most straightforward generalization of this protocol to entangled states would require sort of continuously controlling the entanglement part, which is probably not super easy technically. It would be a challenge in many systems. There might be a simpler way to do it. And again, this is something we just need to look into.
Yeah, interestingly, what you said is, one of the sensor is sensing and emitting a photon, and the other is not sensing, but it is an absorbent. I was under the impression that maybe both requires to be in a sensing mode, emitting light, such that they can be in a superposition, is what I was thinking. But you said, okay, that's interesting.
No, so I mean, they're both sensitive. Sorry, I just mean the state that they're set up in. And in fact, the state that I described is not the one typically that would be used. Typically, it would be a state that is a superposition of all of the sensors in their ground state and all of their sensors in their excited state. So 0 plus 1 for every sensor, but not this one is 0 plus 1, this one is 0 plus 1. It's that all of them are 0 or all of them are 1 in superposition. Setting that up, let me just say that really depends on the details of the technology. And there is a very, very straightforward generalization of our protocol where you treat this state with all zeros, you just call it 0, and the state with all ones, you call it 1, and you just do our protocol with 0 and 1. The problem is what that requires is the ability to do this sort of like entangled control, which might not be straightforward. So there's probably an easier way. We have to figure it out.
Okay. We have a question from CY Sun. He has a suggestion. He would like to hear more extending deterministic benchmarking of 2-qubit gates in a more complex quantum circuits for superconducting qubits of photonic system. That's what. That's a comment for me, maybe, or maybe you can answer that.
Yeah, sorry. Deterministic benchmarking is another project that I work on with Daniel Lidar. Has to do with characterizing when you're trying to do an operation on a quantum bit or on several quantum bits. And let me say we have got this great protocol for doing it when you're doing an operation on just one. We're developing what I think is an even more exciting protocol for when you're doing an operation on many qubits. And we're not ready to talk about it yet because it's not ready yet. But hopefully I will return at some point in the future with super exciting results about how you can characterize multi-qubit gates.
We will invite you back, Eli. I mean, that's a good benchmarking point of view. It's very important as well. Anyway, thank you so much, Eli. It was great talk, and thank you for addressing all the questions.
Thanks for having me.
Let's have the Peter. Could you please put the okay? So this is next week's seminar series table. So next week, January 30th, Sudhagar Pamarthi from UCLA would be giving us the talk. And see you all next week. Thank you.